we are in 3.5, which is rational functions and their graphs. Here are our objectives. Let's start by talking about rational functions. So a rational function are quotients of polynomial functions. So your numerator is a polynomial, your denominator is a polynomial, and obviously the polynomial in your denominator should not equal 0 since we cannot divide by 0. The domain of a rational function is a set of all real numbers except the x values that make the denominator 0. So the domain is the x values, and these are x values that you can plug into your rational function and get a value back out, but you need to be careful of x values that make the denominator 0. Alright, so let's go in our books to page 406. We're going to start by looking at problems 3 and 5. It says, find the domain of each rational function. So number 3, it says, find the domain of each rational function. And we have g of x equals 3x squared divided by x minus 5 and x plus 4. Well, to find the domain, the first thing you need to do, so step 1, is to set the denominator not equal to 0. So set the denominator not equal to 0. And then step 2 would be to solve for x. Three, graph x values on a number line. And then the last thing we're going to do is go ahead and find the domain. And then step 4, find the domain. So let's go ahead and do that. So set the denominator not equal to 0, so x minus 5 and x plus 4 not equal to 0, and that's because you cannot divide by 0. And remember the 0 product principle. If we have two things multiply together not equaling to 0, that means they both cannot equal 0. So x minus 5 doesn't equal 0, and x plus 4 cannot equal 0. So this tells us x cannot equal 5, and x cannot equal negative 4. Now let's move on to step 3, which says draw a number line and place these x values on it. So here is negative 4, and here is 5. And since we cannot equal 5 and negative 4, we're going to open a parentheses to the left and open a parentheses to the right. Parentheses means do not include. And since you're not including the negative 4, you need to include all of this over here and all of this over there. And the same with the 5. Put a parentheses facing to the left and facing to the right. And then you will shade all of this in between. And you have your arrows coming out. And then remember over here off to the left is negative infinity. And off all the way to the right is positive infinity. Which means the domain of this function, if we start at the far left, is negative infinity, comma, and we travel all the way to negative 4, parentheses. You reach a break, so you put a U for union, and then you go from negative 4, and you keep traveling till you hit the 5. Again, there's your parentheses, so put it here, and you're at a break, so again you need a U for union, and then you have a parentheses, 5, comma, infinity. So the domain of this function would be negative infinity to negative 4, union negative 4 to 5, union 5 to infinity. Alright, number 5. So we have h of x equals x plus 7 divide by x squared minus 49. Okay, so since we are finding the domain, it says find the domain, we're going to do the same thing we did before. So the first thing you want to do is set your denominator not equal to 0. So x squared minus 49 does not equal 0. And then you want to solve for x. So x squared does not equal 49. And then how you get rid of a square? You take the square root on both sides. So now you're saying x cannot equal 7 as well as negative 7. And then we draw a number line, place these x values on it. So we have negative 7 and 7. And since it's not equal, you open a parentheses to the left and you open a parentheses to the right on both values. And you shade everything else to the left, in between, and to the right. Okay, and then you can go ahead and find the domain. So start here at negative infinity. So negative infinity, comma, all the way to negative 7, and then a parentheses and a u for union, and then negative 7, comma 7, u, 7, comma, infinity. All right, let's keep going. So arrow notation. We use arrow notation to describe the behavior of some functions. The first one is said the following: x approaches a from the right. So x is approaching a from the right, which means if I had a graph, so let me draw a graph. Okay, and let's say a was right here. Well, if I am approaching a from the right, so x is approaching a from the right, I will be on my graph from the right of a, and I'll just be traveling until I get to a. And the next one says x is approaching a from the left. Well, from the left, I'll be on the graph from the left side, and I'll travel from the left until I approach where a is located. This one says x is approaching infinity. Well, if x is approaching infinity, infinity is way out here, right? So you would get on your graph and you would just follow it, and it's going this way. And the same if I was approaching negative infinity. Get on your graph, and negative infinity is down here. I'm sorry, to the left. It looks like it's going down, but remember, arrow means it goes on forever. All right, let's go back to our books on page 406. Let's look at number 9, 13, and 17. So number 9 says, use the graph of the rational function in the figure to show use the graph of the rational function in the figure shown to complete each statement. Number 9 says, as x approaches negative 3 from the left, remember this negative up here means from the left, f of x is approaching blank. And they left it blank for us to fill in. So let's fill it in. So go ahead in your books, get on your graph. So first of all, let's find negative 3. So find negative 3 on the x-axis. And then what I want you to do is step a little bit away from negative 3 towards the left. Once you have done that, drop down to your graph. So where your pencil or your finger is on the blue graph. And then I want you to follow it. So as x is approaching negative 3 from the left, f of x, which is the blue graph, is going further down, right? What is it approaching down there? Negative infinity. All right, let's look at number 13. So now it says, as x approaches negative infinity, f of x approaches, again, blank. All right, so this time, let's get on our graph. And since we are approaching negative infinity, which means it's going to be in the far left direction, I want you to get on your x-axis. How about all of us start at the origin? Start at the origin, and then start moving towards the left on the x-axis. Keep going all the way over until you reach like the -5 area. And then drop down onto your blue graph and keep going towards the left. So as x is going towards -infinity, that graph, that blue graph, is approaching something. It's approaching the x-axis. And you got to think, f of x is the same as y. So if I was approaching the x-axis, then f of x is approaching 0. All right, one more. Let's look at number 17. Different figure, but same instruction. So it says, as x approaches -2 from the right, so as x approaches -2 from the right, f of x approaches blank. So let's find -2 on your x-axis. Find -2 on your x-axis. And this time it's from the right, so I want you to go over just a little bit from the right and then fall down onto your graph, your blue graph. And then what I want you to do is travel towards -2 on the blue graph. And you'll see that it's going down. It's going further down. The arrow means it's going to go down, which means he's approaching -infinity. All right, now let's talk about the definition of a vertical asymptote. The line x equals a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bound as x approaches a. So what they're saying is that if you have this blue graph and you follow it, it will go all the way up. It's going all the way up because it cannot touch the line x equals a. The line x equals a is a vertical asymptote. And the same if I was coming from this direction. It basically blows up. If it cannot go across the vertical asymptote because you cannot be a, it will blow up. Or it may blow down. When I say blow, I mean as in get larger in the positive direction or get larger in the negative direction. So this one's approaching -infinity as x is approaching a from the right. And as you approach it from the left, f of x is also approaching -infinity. Now let's look at how we find vertical asymptotes. So if p of x divided by q of x is a rational function, and remember rational function means that this is a polynomial as well as this one is a polynomial, in which p of x and q of x have no common factors. If they have common factors, that's what we call holes. And we'll work some problems, hopefully, that have some holes. And a is a 0 of q of x, the denominator, then x equals a is a vertical asymptote of the graph of f. So let's talk about the steps that we need to do to find our vertical asymptote. Step 1 is to factor the numerator and denominator, if possible. Cancel out any common factors between the numerator and the denominator. If they have common factors, those are what we will consider holes. And then step 3 is to set the denominator equal to 0 and solve for x. This will become your vertical asymptote. So let's go back in our books to page 406. We're going to start by looking at number 23. And it says, find the vertical asymptotes, if any, and the values of x corresponding to holes, if any, of the graph of each of the rational functions. So g of x is equal to x plus 3 divided by x times x plus 4. Okay, so the first thing we want to do is see if we can factor the numerator and the denominator. Well, the numerator cannot be factored, and the denominator is already factored. And then we see if they have any common factors between them. They do not, therefore there are no holes for this function. Then our next step is to set the denominator equal to 0. So x times x plus 4 equals 0. And then from the zero product principle, we set each equal to 0. So we have x equals 0 and x plus 4 equals 0, and we solve for x. This one is already solved for us. And this one will become x equals negative 4. Therefore, your vertical asymptotes are x equals 0 and x equals negative 4. If you were to graph this function using your graphing calculator, you'll see as the graph approaches 0, it either blows up or it blows down, but it will never actually touch x equals 0. And you'll see the same behavior when x is negative 4. All right, now let's look at number 29. So this time we have f of x equals x squared minus 9 divided by x minus 3. So the first thing we need to do is factor the numerator and the denominator if possible. Well, x squared minus 9, that factors into x plus 3 times x minus 3, all divided by x minus 3. Okay, so we see a common factor, and that is x minus 3. So let's cancel those out, which means we have a whole at x minus 3 equal to 0. And that's where x equals 3. So you have a whole at x equals 3. Now, once we canceled these out, we were left with just x plus 3 over 1. Well, 1 will never be 0. Therefore, there is no vertical asymptotes. You have a whole at x equals 3, and you have no vertical asymptotes. And then last one, number 33, it has h of x equals x plus 7 divided by x squared plus 4x minus 21. And again, step 1 was to factor the numerator and the denominator if possible. So the numerator stays x plus 7, and the denominator becomes x plus 7 times x minus 4. And then the next step is to factor any cancel out any common factors. So x plus 7 is canceled out, which means we have a whole at x plus 7 equal to 0, which is located at x equals negative 7. So you have a whole at x equals negative 7. And then your rational function will be left with a 1 over x minus 4. So then the next step was to take the denominator and set it equal to 0. And this time we have a denominator. So we set it equal to 0. So x minus 4 equals 0, which means x equals 4 is the vertical asymptote. Alright, now that we're done talking about vertical asymptotes, let's talk about the horizontal asymptote. So the line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. So basically, you notice that your graph is approaching some line, some value that it'll never cross. That is a horizontal asymptote. Same here. You're approaching, and you are approaching. I'm sorry, this way. You are approaching. Now, unlike your vertical asymptote, your horizontal asymptote follows 3 rules. The first thing you need to do is find the degree of the numerator. Then you find the degree of the denominator. They have represented the degree of the numerator with an n and the degree of the denominator with an m. Now, if n is less than m, so basically the numerator's degree is less than the denominator's degree, the x-axis, or y equals 0, is a horizontal asymptote. If they are equal, if the degree of the numerator is equal to the degree of the denominator, then the line y equals a sub n over b sub n is a horizontal asymptote. A sub n is the coefficient, it's the leading coefficient in the numerator. And b sub n is the leading coefficient in the denominator. If the degree of the numerator is greater than the degree of the denominator, then f has no horizontal asymptote. So now let's go back in our books to page 407. And we're going to start by looking at number 43. It says, find the horizontal asymptote, if there is one, of the graph of each rational function. It's number 43. And it has f of x equals negative 2x plus 1 divided by 3x plus 5. So the first thing you need to do is find the degree of the numerator and a degree of the denominator. So the degree for the numerator is going to be a 1 because the highest exponent is a 1. And the degree of the denominator is also a 1. And we notice that these are equal. So by definition, we have a horizontal asymptote located at the line y equals, well, the leading coefficient in the numerator is negative 2, and the leading coefficient in the denominator is 3. So you have a horizontal asymptote at the line y equals negative 2 over 3. Okay, so now that we began talking about rational functions, we can get into the reciprocal function. And there's two of them that we normally work with. F of x equals 1 over x, and f of x equals 1 over x squared. Here are some characteristics about them. F of x equals 1 over x is an odd function. So basically, if you were to do f of negative x, it would be the same as saying negative f of x. I can show you this up here. So f of negative x, everywhere I see an x, I'm going to make it negative x. It's going to be 1 over negative x, which is the same as saying negative 1 over x, which is the same as saying negative f of x, as originally he was 1 over x. So it's an odd function, and it has origin symmetry. Basically, it's a mirror image. If you were to flip it across the origin, you have the same image. F of x equals 1 over x squared. Well, it's an even function. So again, if you were to plug f of negative x, so everywhere you see an x, make it negative x. Well, that's 1 over negative x squared, which is still the same as 1 over x, which is f of x. And it has y-axis symmetry. You notice that they look like mirrors. It's like a flip over the y-axis. Okay, so let's use transformations to graph a rational function. We're going to start by graphing f of x equals 1 over x. And we're going to then graph g of x, which is going to be 1 over x plus 2 minus 1. Okay, so with your graphing calculator, you can graph 1 over x. It has a horizontal asymptote at the line y equals 0. And it has a vertical asymptote where at the line x equals 0. And of course, we're going to grab a few points. So we grab the points, a couple points, 1, 1, and negative 1, 1. You can plug 1 in for x, and you'll get 1 back for y. Plug negative 1 in for x, and you'll get a negative 1 back for y. Alright, so remember how we did our transformations. If it's a change on x, you do the opposite. If it's a change on the function, you follow that change. So the first thing we're going to do is work with the change on x first. So this says add to, which tells us to shift the graph 2 units to the left. Always do the opposite if it's a change on x. And then the negative 1 tells us to go down 1 unit. So let's take our points, 1, 1. And if we make the change on the x and the y, well, the 1 for the x will become negative 1, because remember, shifting 2 units to the left is like saying subtract 2 off of the x. And then go down 1 in the y direction makes it a 0. And let's do the same for the other point, negative 1, negative 1. Shift 2 units to the left makes that negative 3. And then go down 1 makes that negative 2. Okay, so what they did was they first started by doing the change on x first. And then they finally made the change with the change on y. So the original points were 1, 1, and we said they would become negative 1, 0, and then negative 3, the other point was negative 1, negative 1, and it became negative 3, negative 2. And of course you can plot them. And let's talk about how the horizontal vertical asymptotes change. The vertical asymptote before was x equals 0, and the horizontal asymptote before was y equals 0. When we shifted 2 units to the left, the vertical became x equals negative 2, and when we went down 1, the horizontal became y equals negative 1, as we see here. Alright, let's go in our books to page 407. Let's look at problem 55. It says use transformations of the graph f of x equals 1 over x or f of x equals 1 over x squared to graph each rational function. So we're doing 55, and it has h of x equals 1 over x minus 3 whole thing squared plus 1. So the first thing we want to do is go ahead and graph f of x equals 1 over x squared. Now we know we're going to do 1 over x squared because we have a square here. We want to match up. And remember, this one looked like, if I can sketch it correctly, it'll be a little off. Let's pick a different color. And what we're going to do is basically pick some points off of it. So let's pick the point 1, 1. Now how do we know that point is there? Because we can plug 1 into the function and we'll get 1 back. And let's also pick the point negative 1, 1. Again, plug negative 1 in for x and you'll get a 1 back. This has a vertical asymptote at x equals 0. And it has a horizontal asymptote at y equals 0. Okay, now using this graph, we're going to do our transformation. So let's start with the change on x. So it's telling us to subtract 3, which means we're going to shift 3 units to the right. Remember, always do the opposite when the change is on x. And then the plus 1 tells us to go up 1 unit. So we started with our points 1, 1 and negative 1, 1. Well, shift 3 units to the right will make this 4, and then go up 1, make it 4, 2. And do the same with the negative 1, comma 1. 3 units to the right will make this a positive 2, and going up will make it a 2. Now, how does the vertical asymptote and the horizontal asymptote, how do they change? Well, before x was equal to 0 was our vertical asymptote. We're shifting 3 units to the right, so now it's going to be x equals 3. And your horizontal asymptote was y equals 0. Now it's going to be y equals 1. And let's see if we can graph this. And of course, this would just be a sketch. Okay, so we have the points 4, 2 and the point 2, 2. We have a vertical asymptote at the line x equals 3, so let's draw a dashed line right here down. And we have a horizontal asymptote of the line y equals 1, so let's draw a dashed line. And then let's do our best to connect. Remember, the shape is still the same. All it did was move a little bit. And be careful not to touch the asymptotes. And this is what your graph should look like. Now you can verify by graphing this with your graphing calculators. If you need help with that, just email me and I'll talk you through it. Alright, so these are strategies for graphing a rational function. I am not going to read through them. I'll let you read through them. And if you have questions, please email me. Okay, so now we're going to talk about slant asymptotes. The graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So if the degree of the numerator is 1 more than the degree of the denominator, it has a slant asymptote. Okay, so how do you find the slant asymptote? Well, you just divide Q into P. So what you're going to do is use synthetic or long division to divide P of x by Q of x. Let's go in our books to page 407, and we're going to look at number 81 and 87. So 81, it says find the slant asymptote, and then it wants you to graph. We're just going to find the slant asymptote, and I'll leave the graphing to you, and you may use your graphing calculators. So it says f of x equals x squared minus 1 divided by x. So the first thing you need to do is realize that the degree of the numerator is 2, and the degree of the denominator is 1. Well, the numerator is 1 more than the denominator, so a slant asymptote does exist. And to find it, we're going to divide. Now, let me erase that 1 because it looks like a 2. We're going to divide, so I'm going to use long division. So you're going to have x squared minus 1 divided by x. So x squared minus 1 divided by x. Now, since we're dividing, let's go ahead and be careful. We're missing a term, so when we miss a term, let's make sure we plus 0x in there, and then subtract the 1. So x squared divided by x gives us x. X times x is x squared. subtract, these cancel, that 0x falls down, and so does the I'll just say the 0x falls down. So then 0x divided by x was just 0, so I'm going to put plus 0, it really doesn't matter. And then we get 0x, subtract, they cancel, and then negative 1, there's your remainder. So you have a remainder of negative 1. If I went too fast for the long division, email me and I'll explain how to do it again. So in this case, let me erase that 0 since he was just a placeholder. So when I divide these, I have x plus negative 1 over x. And of course, you should verify that you get what I get. Now, the slant asymptote is going to be the line y equals just x. What you do is you ignore the remainder piece. Ignore the remainder, and the rest is a slant asymptote. So this has a slant asymptote at the line y equals x. Let's look at number 87. This time we have f of x equals x to the third power plus 1 divided by x squared plus 2x. And again, we're going to use long division, so x to the third plus 1 divided by x squared plus 2x. And again, I forgot my placeholders, so let me put those in. And let's divide. So x to the third divided by x squared is just x. Multiply, that gives me x to the third plus 2x squared. And then I want to subtract, so I change the sign here, and I change the sign here. Those cancel, get a negative 2x squared plus 0x. And then I repeat, negative 2x squared divided by x squared, well that's just negative 2. And then we multiply. And we're going to subtract, which means we change our sign, so this is a plus, and this becomes a plus. Those cancel. Now I have 4x, and we drop down the plus 1. So this piece right here, this 4x plus 1, is now our remainder, because 4x cannot be divided by x squared evenly. So we have a remainder of plus 4x plus 1 all over x squared plus 2x. Now again, you ignore the remainder, so ignore the remainder. So ignore the remainder, and your slant asymptote is located at y equals x minus 2. Okay, this concludes our video for 3.5. Please email me if you have any questions.